We'll rediscover integration today, put it on a differential geometric footing, if this works, okay? Remember, we addressed earlier the question, why are differential forms special? After all, they are just totally antisymmetric covariant tensors. What's special about them? Why not totally symmetric, antisymmetric contravariant tensors, or symmetric ones, or arbitrary ones? And I mentioned already that what is special about them, about the differential forms, is that they have a particularly useful transformation property under change of charts that makes them uniquely suited for integration. In particular, a 2 form will be integrable over a 2-dimensional manifold, an S form over an S-dimensional manifold. However, there is a little subtlety that can arise that we need to address first, which is that there can be minus signs. There is an ambiguity in principle. And that's because, roughly speaking, because they're left-handed and right-handed coordinate systems. And if you change from one to the other, you pick up a minus sign. And it turns out that this is not just a matter of, well, do I choose this sign or that sign? No, there's a matter of consistency too. Let us define the notion of orientation of a manifold. Consider, for example, a 1-dimensional manifold. So it's just like a line here. It goes from a starting point P to a point Q. That's our manifold. And how does a chart look like then? Well, the manifold is 1-dimensional, so the charts will map on R1. Here's a picture of R1, of just R, the real line. And we have a chart that is mapping, for example, the point P into this small number and the point Q into that large number. And this chart alpha is mapping points in between into numbers of in-between size. But we can also choose another chart for this manifold, and that chart would map the point P into the largest number of the interval, and would map the point Q into the smallest number of the interval, and numbers in between, into points in between, into numbers in between. So there is some fundamental change between, some fundamental difference between the chart alpha and the chart beta here. But this sort of thing will make a difference, because after all, we want to express integration over an abstract manifold in terms of integration on Rn, which we already know how to do using Riemann and Lebesgue methods. But you can see here that if we want to express integration over this 1-dimensional manifold in terms of integration over R, well then you see there's an ambiguity here, because whether I integrate from A to B or from B to A makes a difference of a minus sign. And ultimately, this is because the change of variable from this coordinate system to that coordinate system, let's say this variable is called t, and that variable is called t prime, then by the chain rule, as we change variables, we get a factor of dt by dt prime, which is -1, because the one is growing while the other one is diminishing as we change coordinate system, right? The change of coordinate system map has this property that its chain rule factor is -1. Now for n-dimensional manifolds, how does that look like? First of all, we may need, in the first place, we may need several charts. It can happen that a manifold cannot be covered by one chart. We need several of them. So we need a few definitions. A complete collection of charts, which is to say an atlas for a manifold, is called oriented if among all the overlapping charts, whose coordinates we may call x and x tilde, the Jacobi determinants are positive. The Jacobi determinant plays an important role in n-dimensional integration because as you change variables, the chain rule produces a Jacobi determinant. And a manifold is called orientable if it possesses an oriented atlas. This is not trivial. They don't always possess an oriented atlas. For example, a Möbius strip, Möbius strips are not orientable. This thing has only one side. A manifold with a manifold M together with a choice of oriented atlas is called an oriented manifold. And then an arbitrary chart is called positive or negative with respect to this orientation of the manifold if its Jacobian determinant with respect to the charts of the atlas is positive or negative. This means that you choose for your manifold, if it's an orientable manifold, choose a complete covering of it in terms of charts, which all have positive Jacobian determinants as you change charts. And then after you've done that, after you've made the manifold an oriented manifold, then you're free to choose any coordinate system you want, even ones with other-handedness. And then you know when and when not you're picking up a minus sign because of the sign that comes up with the change of coordinate system and the Jacobian factor. And you see, if the manifold were not orientable, then there is no unique sign. You can still locally integrate, but there's no unique sign, no globally defined sign for your integrals. Now here's a nice theorem that will be very useful for general relativity. First, the definition. On an n-dimensional manifold, a differential n form omega is called a volume form if it nowhere vanishes. And you can use the volume form to do what the name advertises. You can use it to define a notion of volume. You can, for example, integrate it over to obtain the entire volume of the manifold. We will later find that in general relativity, we automatically always get a volume form. But you may want to keep it in the back of your mind, if you're interested in quantum gravity, for example, that the notion of volume form is, in principle, as far as differential geometry is concerned, independent of the notion of metric. If you have a metric on your manifold, and we will get to this today, then you automatically also get a volume form. But you don't, in principle, have to use that volume form. You could choose another volume form. The notion of length, in principle, as far as differential geometry is concerned, is independent of the notion of volume. It's a weird thing, but yes, you can do that. It's not usually done. Usually we use the volume form that comes from the metric. And that's important because of the next proposition. The proposition says that if a manifold possesses a volume form, and in general relativity, because we assume there is a metric, and therefore we always have an induced volume form, we can conclude that the manifold is orientable. So we don't need to worry about that in general relativity. If we have a metric, then orientability can be taken for granted. So let's come back to integration now that we've clarified some issues with the orientability. Consider n-dimensional integration as it is usually done without differential geometry, just in Rn. Yep?
What about the reverse? Let's say you're not looking for a metric, you find a volume form without a metric.
Yes, exactly. Yes, exactly. That's the case. You can have a differentiable manifold on which no metric is defined, and still have a volume form on it.
So volume forms are more generalized?
They are, yeah, in a sense, yes. You can have manifolds that have a notion of volume without having a notion of distance. Who knows? Maybe this sort of little loophole in differential geometry is useful somewhere. Nobody's used it yet, but I just want to point out that it is there. Okay, so ordinary integration in Rn, as you've seen it many times before. So here's an integral over Rn. And don't think of this as a differential form here. Just think of it as the usual notation for n-dimensional integration, arrived at through Fubini's methods and so on. So this is just ordinary integration of a function on Rn. G is a function on Rn. And we're talking here about Riemann or Lebesgue integration of that function over Rn. What happens if we change coordinates? If we change variables? If we change variables away from the variables x to variables x tilde. Let's say the variables x are functions of the variables x tilde. But then we can express this integral, assuming that the map is mapping Rn into Rn, so that we don't have to worry about boundaries. Then we can express this integral here by re-expressing this function in terms of the new variables. So it's g of x, but the x are functions of the new variables x tilde. And we know from the usual methods of Riemann and Lebesgue integration that then for this number here to be the same as that number there, for the value of the integral to come out the same, we cannot simply change the integration variables. No, we have to take care of this chain rule factor, which actually is the determinant of the matrix of the chain rule coefficients, where you differentiate each variable with respect to each other variable. And maybe it wasn't completely clear in the Riemann or Lebesgue case where that determinant comes from, but we will see now from the differential geometric perspective how a determinant arises. But let us just take this for granted. This is how integration in Rn should work under change of variables. But from the differential geometric point of view, this is important to know, because when we integrate over a manifold, we always want to reduce this to integration over Rn using a chart. But then for this to make sense, it must be independent of which chart we choose. Otherwise, we're doing something that has to do with the coordinate system. But the physics surely doesn't care about the coordinate systems. So if we want to define integration over an abstract manifold, in terms of integration over Rn, it must be chart independent. And that means that we must build in this behavior under change of chart. If this is an integral over, if this is to represent the integral over an abstract manifold in a chart, then that must represent the same thing if we change charts. Now let's consider an n-dimensional differentiable manifold, M, which is not Rn in general, but just some general n-dimensional differentiable manifold. And let us consider an n-form omega on that manifold. So it's a maximum degree form on the manifold, n-form. And as we discussed earlier, these are the ones that can be integrated over n-dimensional manifolds. We integrate 3 forms over 3-dimensional manifolds, n forms over n-dimensional manifolds. Remember that there's only one kind of n form on a differentiable manifold, if n is the dimension of the manifold. They all look like this. Here we have a basis of the tangent space, the cotangent space. This single vector here is a basis of the space of n forms. If you remember, there's only one, at every point of the manifold, there's only one basis vector in the space of n forms, and it can be put into this form. And that's because if there were equal indices occurring, then by the anti-symmetry of the wedge product, these terms would vanish. Also, if the indices 1, 2, until n were to occur in a different sequence, then it would still be the same thing as that up to possibly a minus sign. The minus sign is there if the number of permutations that you need to get there is odd. Otherwise, it's a plus sign. So a general n form on an n-dimensional manifold always has this shape. There is some number-valued function, which is an element of lambda 0, multiplying this basis vector in the space of n forms. This thing we want to integrate over our n-dimensional manifold. Now, if this is representing our n form in one chart, see, we've used a chart here to be able to write it down in the basis that comes with a chart. Then how does this very same differential n form look like if we choose a different chart? Well, if we choose a different chart, then the x go into the x tildes. This is what we achieve here. And since the f is an element of the space of zero forms, just an element of space of functions, we are simply replacing the argument here, so x of x tilde. But we also have to transform all of those basis vectors. Each one of them gets transformed because we now choose a different basis in the tangent, in the cotangent space. We're going from the basis of the dx to the basis of the dx tilde. So each one of them, dx1, for example, goes into a sum over, linear combination of all the dx tildes. For example, dx1, after change of variables, becomes this thing. This matrix contracted with dx tilde I1. See, this 1 is inherited from the dx1 up there. And here we're summing over the I1, dx tilde I1. And similarly, the dx2, the change of variables and the change of chart becomes the linear combination of the dx tilde I2 with these. That 2 stems from the dx2 up there. So we get these matrices here, n of them. And here we are summing over all I1, all I2, all IN, which means that all possible combinations of the basis vectors of the cotangent space occur. Most of these terms just vanish because indices will occur multiple times. All those terms go away because of antisymmetry. The only terms that survive in this expression here are terms where the numbers 1 to n each occur exactly only once. They may occur in different sequences, but they all occur exactly once. So that, for example, there's one term where this is 1, this is 2, this is 3, and so on, up until this being n. That term survives. The other terms that survive are exactly like this one. They differ only by a minus sign or possibly a plus sign, depending on what permutation they are coming from. So actually, all the surviving terms are multiples of dx tilde 1 wedge to the dx tilde n. So we might as well just write that. And then sum up all those terms and keep track of the minus signs that we occasionally get. And this is the result of it. This sum here turns into that. We have one term where it's dx tilde 1 and then dx tilde 2 up until dx tilde n. All the other survivors are the same thing up to permutation. We write them all like that, possibly with a minus sign. And if you do that, because the minus sign occurs if and only if it's an odd permutation that gets you there, you get exactly the conditions for determinant. The product of all the entries of the matrix, if all the entries are chosen differently, and a minus sign is put there if it's an odd permutation. So it's exactly the determinant that arises there. So what we see is that a differential n form under change of chart picks up the determinant of the Jacobian matrix. Let us compare that with the equation from ordinary Riemann-Lebesgue integration. We see that there, what's under the integral, under change of chart, under change of variables in this case, picks up that very same factor here. So that's our signal. It means that we can define the integral over n forms of n forms over an n-dimensional manifold in this way. So let's assume M is an oriented n-dimensional manifold. And let's say that omega is an n form, which in a chart takes this shape. Then let's assume that one chart suffices. We define the integral over the manifold of the n form, or the n-dimensional manifold, the n form, to be what you get when in a chart, or in the chart alpha here, you are integrating this f of x in the usual Riemann-Lebesgue way, where alpha of m is the image of the manifold in Rn. It doesn't have to be all of Rn, right? Of course, sometimes it happens that the manifold cannot be covered by just one chart. In this case, you just piece it together. Then the integral over the manifold will be a sum over integrals like that, piece by piece, where the integrals cover pieces of the, cover images of pieces of the manifold, which together cover the manifold exactly once. And because we assumed it to be oriented, there's no ambiguity in which charts you use, because the minus sign is taken care of. And also, which chart you use for whatever patch you're looking at doesn't matter, because as you change chart, you're picking up a Jacobian factor, but that's exactly what you would expect from the Riemann-Lebesgue in the notion of integral. So you really get the exact same number for that integral, independently of how you integrate it in a chart or in several charts. You can cut it into several charts, and even the charts themselves you can swap out, and you always get the same number. So this is the reason why differential forms are important. And for example, if we had anti-symmetrized contravariant tensors, what would have happened? We could have done the very same thing, except we wouldn't have gotten the determinant of this, but the inverse of it. That would have screwed it up. Now let's move on to the boundary operator. I think I mentioned it briefly earlier. See, we want to be flexible with the dimensions. If you have an n-dimensional manifold, you don't want to integrate only over n forms. There are sub-manifolds of lower dimension, and you can then, let's say, dimension r, and then you should be able to integrate an r form over that. Stokes' theorem, which is where we are heading now, is relating n-dimensional integrations to n-1 dimensional integrations. And for that, we need the boundary operator. So let's say that G is a region in the manifold, which means that it's of the same dimension as the manifold, it's n-dimensional. It's an open and connected subset. Then consider, let's say it's Rn, and you consider a ball in that, an n-dimensional ball in that. Then we denote the n-1 dimensional boundary of that region G by del G. So for an n-dimensional ball, that would be an n-1 dimensional sphere, the boundary of the ball. So we say that this operator del is mapping the region into its boundary. And we say that the boundary of G, the boundary of the region, is smooth. That's something that we will assume for convenience. Is smooth if locally there exists a chart that maps a patch of the manifold into Rn, such that the boundary of our region gets mapped into just a plane. So if it can be straightened out by a suitable chart, then we say that the boundary is smooth. It has nothing to do with the absence or presence of curvature, right? This is just a matter of coordinate system. This is saying that there is a coordinate system such that the boundary of the region appears flat in Rn. That's all. Now we get finally to Stokes' theorem. A little proposition that's useful. If M is an orientable manifold, and again, remember, we are guaranteed that this is so in general relativity because of the existence of a metric which induces a volume form. So if M is orientable, then any region within it is also orientable. That's obvious because it's a less stringent condition on the charts. And also the orientation on the region induces an orientation on the boundary of the region. Now we have all the ingredients for Stokes' theorem. Stokes' theorem being one of the most important theorems in mathematics, and certainly one of the most beautiful. By the way, Stokes' theorem, if you're coming from physics, then you may have seen Stokes' theorem first in the context of electrodynamics, where it has to do with the curl, and it's usually said, well, there's Stokes' theorem, that's great when you work with curls. And then there's Gauss' theorem, and it has to do with divergences, and so on. And then you may have heard of Green's theorem, which applies in two-dimensional settings. And then you may have heard of contour integration in complex analysis, where you integrate and you have to worry about residues and so on. All of these are the same. All of these are examples of this. This is the super Stokes theorem that includes all of the others. And we will see today how that comes about. So here is the Stokes theorem in its abstract formulation, in its most general formulation. So assume that your region G is well behaved. Technically, its closure has to be a compact n-dimensional region. So for example, if you had a disk, then it would obey those conditions. But if you have this disk and you make it grow an infinite number of spikes that go out to infinity, then it would not match that condition. But generally, for physical purposes, our regions always obey those conditions. So here's Stokes' theorem. What it says is that if G is an n-dimensional region, and del G is its n-1 dimensional boundary, then the integral, the way we just defined it, through charts, but chart independently, the integral of this differential form over the region G gives us the same number as integrating that differential form over the boundary. And the interesting thing here is that omega is an n-1 form. It's got to be because that's an n-1 dimensional manifold. So this has to have the same degree as this has the dimension. So omega is an n-1 form. Then d omega is an n form, which is all right because we need to integrate it over an n-dimensional manifold. So this is an n-dimensional integral over an n form. And this is an n-1 dimensional integral over an n-1 form. And notice this beautiful symmetry here, which is that here we have a del operator that gets us the differential of a region. It gives us the boundary of a region. It gives us the place where the region could grow or shrink. This gives us the boundary of a region. Whereas the d operator, which we earlier already called the co-boundary operator, gives us the exterior derivative of a differential form. So basically the way you can read Stokes' theorem is, one moment please, the way you can read it is that if you start with this and you want to get rid of the del here, you can do so, but then you have to put the co-boundary operator over there. Vice versa, if you're dealing with an integral of that form, then you can get rid of this exterior derivative here by putting instead a boundary over there. Okay? So you get a choice. Either it's the co-boundary operator or the boundary operator that you have acting here. Mm-hmm.
Just wondering if there has to be, if there are any restrictions to G, like if G has to be smooth or... W.
It has to be a compact n-dimensional region.
That's the only restriction.
Yeah. Yeah. Remember that you know, you're not differentiating the boundary itself or anything. You're integrating over it.
Also on W, if there is a restriction on W, maybe it has to be.
Oh yeah, of course. Our differential forms, we always assume them to be smooth. Yeah. I mean, you can get away with less differentiability than that, but for our purposes, let's just not worry about whether it's 5 or 6 times differentiable. Let's just assume it is smooth, infinitely many times differentiable.
What if I was wondering if G is not orientable, then if you're...
Well, then the sign wouldn't be unique. If it's not orientable, you can always locally still integrate, but there's the sign is just not unique anymore. Okay, so here we have Stokes' theorem. Isn't it nice that you can get rid of an exterior derivative by putting a coboundary there, a boundary operator there, or vice versa? You can get rid of this by putting that there. Now, isn't that tempting? If this relates n-dimensional integration to n-1 dimensional integration, well, what if we just iterate that? Doesn't that relate it to n-1, n-2 dimensional integration, then n-3 dimensional integration, eventually 0 dimensional integration, which hopefully is trivial. And then all integration is trivial. That would be nice. Well, we're not so lucky, but we will learn something very interesting by trying that out. So let's try to iterate Stokes. Let me show you Stokes while I show you the other thing. Okay, so we assume now that G is itself the boundary of H. Okay, so in this way, we can take Stokes' theorem and extend it to the left. So let us rewrite Stokes' theorem, but replacing G by del H. Okay, we're assuming that G is del H. Okay, so what do we get then? Then we have, oh, I hope you can see both. So up here is Stokes' theorem, and down here I'm writing, this is Stokes again. Just the same thing. I've only replaced G by del H, and then del G becomes del H. Okay? Otherwise, it's exactly the same formula. But now, we can see here that we have a d omega here with del H. And using Stokes again, whenever we have a del G, we should be able to get rid of that del by putting another d in front of the differential form. So let's do this. We have a del here, and we use Stokes to get rid of the del in front of the H at the expense of having an extra d in front here. What do we get? Well, we get 0 equals 0. Because d squared is 0, always, on all differential forms. But also, as we discussed earlier, the boundary of a boundary always vanishes. So that's always also the 0 manifold, just no point. So we get 0 equals 0. But for a quite deep reason. Remember that this is algebraic. It has only to do with symmetrization and anti-symmetrization. Nothing geometric goes into proving that d squared is equal to 0. This is entirely geometric, the fact that boundaries don't have boundaries. So what the message here of the Stokes theorem is that Stokes theorem says that if you have d squared is equal to 0, then you have del squared is equal to 0. If you have del squared is equal to 0, then you have d squared equals 0. So Stokes theorem is relating the two. And that's pretty deep, because that's completely geometric, that's completely algebraic. This little sketch is just to say that if you take, for example, half an eggshell, then its boundary is a circle, but that circle doesn't have a boundary. Just to illustrate that del squared is the empty set. So this observation justifies calling the d the co-boundary operator when del is called the boundary operator. Now, special cases. I listed a few cases earlier, and let's go through them. let's start very simply with the fundamental theorem of calculus. Let's assume the manifold is R. And the region in the manifold is just the interval from A to B. Then what's the boundary? What's the boundary of the region G? Well, it's just the two endpoints. That's the boundary of the region G, of the interval. So Stokes' theorem, which is this, takes a particular form. You see, here we have f is a function. Function is a zero form, right? And then the df is a one form. And one forms can be integrated over one-dimensional manifolds. This is a one-dimensional manifold. We can integrate this one form over it. And by Stokes' theorem, that's the same as the integral over the boundary of our one-dimensional region, which is zero-dimensional. It's the set of 2 points. Each point is zero-dimensional. Each set of points, each discrete set of points is still zero-dimensional. So it's the integral over this zero-dimensional set of points of just a function. A function is a zero form. That's a zero-dimensional manifold. How does that play out explicitly? Well, it's simply this, the fundamental theorem of calculus. df, the differential of a function, is integrated over the integral from A to B. So the integral from A to B of df, and you may know it in the more familiar notation of df being df by dx. In other words, it's f prime dx. It's the derivative of f that we're integrating from A to B, and that by the fundamental theorem of calculus is the evaluation of f of B minus the evaluation at A. So in the one-dimensional case, we get the fundamental theorem of calculus. That's just Stokes. Let's look at the special case where the manifold is R2, and the region in the manifold R2 is some compact region. It has some closed boundary curve del G. That it is closed is trivial, by the way. Remember that the boundaries don't have boundaries. So we're dealing here with a two-dimensional region in R2. We want to integrate a two form over that. Yep?
Just on the previous page, page 12,
Mm-hmm.
it said for Stokes' theorem, the conditions for the manifold has to be compact manifold. But
The boundary has to be compact. The closure of it has to be compact, right? Right. So if the closure G bar of G is compact, and yeah, good observation. The interval wasn't closed, but
Think about that.
Okay.
So G bar has to be a region as well, right?
Yep.
But I just regions were open.
Hmm?
Aren't regions open? G bar would be closed.
I don't remember exactly how we defined that, but you can always close them. And the condition on Stokes is that the closure has to be compact. Okay, so let's move on from 1 to 2 dimensions. We're looking at a two-dimensional region in R2. And the only thing that we can integrate over that is a two form. And then we will relate that using Stokes to a one form and integration over a one-dimensional manifold, namely the boundary of this two-dimensional region. So let us consider a differential one form, omega. Omega is some coefficient function omega 1 times basis vector of the space of the cotangent space plus some coefficient functions, the other basis vector of the cotangent space. Any one form can be written in this way. The exterior derivative of the one form is a two form. That's the thing that we want to integrate over the region. So the exterior derivative of this one form is obtained by applying the Leibniz rule on these. And remember, we did this earlier. This is the outcome of that. You get the minus sign because in principle you would have it the other way around for the second term, but then you use the anti-symmetry. And you can put it in this way. Okay, so we have a 2 form, we have a 1 form. And Stokes' theorem says that if we integrate the 2 form, the d omega, over the 2-dimensional region in R2, then you get the same number as if you integrated the 1 form omega over the boundary of that 2-dimensional region. Let's plug it in. So we have here the 2 form that we integrate over this 2-dimensional region in R2. I'm indicating that with 2 integral symbols, but really it wouldn't be necessary. It's just a tradition to do that. And that, by Stokes' theorem, is the same as integrating over the boundary of that region, this 1 form. This theorem you may have seen earlier under the name of Green's theorem. You may think, well, okay, that's nice, but it's 2-dimensional. Nature has more dimensions than that. But it turns out that Green's theorem is also giving you contour integration. I'm not spelling this out. I'm not sure if all of you have done complex analysis or are very familiar with this. I leave it to you to explore that. The thing is that you can view the complex number plane as R2, of course, and then play with it a little bit. Some of you may be already familiar with this. If not, try it out. It turns out that Green's theorem is really contour integration. And that the Cauchy-Riemann equations that you use to check for analyticity of a function, for holomorphicity, Cauchy-Riemann equations are just equations that express the condition for a differential form to be closed, but not necessarily exact. And that's how you get residues. So again, a complex integration is a special case of Stokes' theorem. Special case number 3. This is the case in which Stokes' theorem comes up in electrodynamics and is called Stokes' theorems there. Let us consider the manifold R3. And then Stokes' theorem also takes this form, where we integrate over a region in R3 a vector field, but actually not the vector field itself, but the curl of it, where this nabla vector is in electrodynamics usually defined in this way. And by the traditional Stokes' theorem, as it is used, as the terminology is used in electrodynamics, this is the integral over the boundary of the 2-dimensional boundary of that region over just the vector field itself. And it turns out that that traditional 3-dimensional Stokes' theorem is a general case of our Stokes' theorem, of the general Stokes' theorem, where the omega or W is really a 1 form, and then what is the cross product of the nabla field with the omega? Well, it's just the exterior derivative. If you remember, if you take a 0 form and apply the exterior derivative on that, you get the gradient. If you take a 1 form and apply the exterior derivative on that, then you get the curl, if you do that in 3 dimensions. In other dimensions, you get something else. But in 3 dimensions, applying the D to a 1 form gives you what in electrodynamics is called the curl. That's important because it means that this thing here is really the D of a differential form omega. But when you integrate the D of a differential form, then you can apply Stokes' theorem, get rid of the D, and have a boundary operator instead. And that is what you get here. You get rid of the D here. This is the D omega, so that you just integrate over omega with the boundary there. Okay. Now in electrodynamics, also Gauss' theorem comes up. Now Gauss' theorem doesn't follow immediately from the general Stokes' theorem. There's one more ingredient needed. And that's the divergence of a vector field. Once we've defined the divergence, then we can apply that to a Stokes theorem, and then we will get Gauss's theorem out of it. So what is the divergence? Well, in order to define the divergence, we need a volume form. It won't be immediately clear why a volume form, or maybe it won't even later be clear, but I try my best. We will make a definition for the divergence of a vector field, which is covariant in the sense that it is chart independent and can work under any circumstances. It's an abstract definition. And then we show that this abstract definition, even though it looks a little involved and perhaps a little contrived, does the job in the special case where we know what the divergence of a vector field is. So basically, we create our definition for the divergence by saying it has to obey two conditions, and then hope for uniqueness. One condition is it's got to do the divergence job on Rn, where we know what divergence does. And secondly, it's got to be completely covariant and coordinate system independent. And then that should be unique. Okay, so the divergence of a vector field psi is defined with respect to a volume form omega. That makes it look like it's ambiguous, and it is ambiguous because it depends on what volume form you choose. But remember that in general relativity, that's not a problem because the volume form will be taken from the metric. The metric, the notion of length, will induce a notion of volume that we will use, and the divergence will always be defined relative to that notion of volume. But so far, we haven't really introduced the metric, so we work with a general volume form. Then the divergence of a vector field psi, a tangent vector field psi, with respect to a volume form omega, is given by the Lie derivative of the volume form in the direction of the volume field psi, of the vector field psi. It's not obvious why that would have to do anything with divergence, but let's test it out. Clearly, it's something canonical, right? You've only introduced canonical things. It doesn't refer to any coordinate system in particular. So mathematically speaking, it's canonical. General relativistically speaking, it's covariant. So let's wait a moment. Before we subscribe to that definition, let's check that it does the proper job wherever we know what the divergence should be. Remember that the divergence, at least on Rn, when there are no further complications present, then the divergence of a vector field is what you get when you take the components of the vector field, differentiate the first component in the first direction, add to that what you get when you differentiate the second component with respect to the second direction, etc. Right? So it's just nabla dot psi. Or in Einstein's shorthand notation, it's psi I, comma I. So you differentiate psi, the vector field, with respect to the i's coordinate, and sum over all I. This is the divergence as we know it from electrodynamics on Rn. Let's see whether we recover that from this definition up here. So let's assume our volume form takes this form. It's not really an assumption, it's just a notation, because all volume forms must take that form, because all n forms take that form, right? Remember what a volume form is? It's an n form that nowhere vanishes. So because omega is a volume form, it takes this form, and a of x nowhere vanishes. It's a function in lambda 0. And let's say that our vector field is expanded in this way. We choose the canonical basis in the tangent space. These are coordinate functions, and these are the basis vectors. Then what do we get from this formula up here? That the divergence of the vector field is the Lie derivative of omega in the direction of psi. Well, by definition, the divergence of the vector field is the Lie derivative of the volume form in the direction of psi. And what is that? If you remember, the Lie derivative of a tensor is obtained by differentiating the function in front and then also having extra terms where the psi gets differentiated. We did this at the end of the last lecture. So we get psi of A, which is, when you spell it out, psi I, and then the partial derivatives of this coefficient function in the various directions, times that. And then, basically by the Leibniz rule, we leave the A the same. Not basically, it is the Leibniz rule. And we leave the A the same. And then we have to apply the Lie derivative here. Right? So again, the Lie derivative of omega by the Leibniz rule is given by the Lie derivative acting on the coefficient function, leaving the rest the same, plus leaving the coefficient function the same and applying the Lie derivative on all of the terms separately, lots of terms there. The Lie derivative on the coefficient function is the directional derivative on the coefficient function, but the directional derivative is just the tangent vector applied to the function, right? Directional derivatives on functions, we know what they are. They are just the tangent vectors, and that's the same. Lie derivative on a function is just evaluation of the tangent vector on the function. Right? Lie derivative is just a generalization of directional derivative to all differential forms, to all tensors. Okay, so by the Leibniz rule, we have these two terms. Here we have the Lie derivative of a basis vector. What do we get? What is the Lie derivative of such a basis vector? So the Lie derivative of a basis vector of the cotangent space in the direction of psi. Remember, that's the directional derivative of an exterior derivative. And we said that was the part of the construction. That's the same as the exterior derivative of the directional derivative. Right? We said that those two commute. Okay, so the Lie derivative applied to a cotangent vector is the exterior derivative of the cotangent vector acting on psi, which is the directional derivative. Let's spell it out. The psi acting on that function is this tangent vector acting on that function. But you see, we can work out what that is. The tangent vector here acting on that function, on these coordinate functions, then this will give us a Kronecker delta here. So we get a d of the psi j Kronecker delta ij. And we're summing over all j. Of course, we pick up only the term with I here because of the Kronecker delta. So we just have d of psi I. And the psi I, are the coefficient functions of the vector field. They are in general position dependent. And so the differential of these functions, of these coefficient functions, is d psi I by dxr, dxr. It's just the differential of a function, the function psi I. However, this is a sum which involves all the cotangent basis vectors, but only one of them is going to survive in this environment because this is totally anti-symmetric, and this has to be, the only term that survives in here is the term that has the index I, because that's the only one that's not taken yet. Otherwise, we get an index twice occurring, anti-symmetry kills it. So out of that sum, only this one term survives where we have d psi I by dxi. So overall, what we get is that the Lie derivative in the direction of psi of omega is given by this first term here, that's this, psi I coefficient, and then the derivative of the coefficient function in the ith direction, plus leaving that the same, and then you get the psi I, I coefficient for all of those terms as you go and perform this calculation here, there, and so on. This is this sum I equal 1 to n. You get the Lie derivative acting on each of those in sequence. So the upshot of this is that we can write the divergence of a vector field as 1 over a, and then within brackets, a times psi I differentiated in the I direction. Why is that so? Well, let's see. A psi differentiated by the product rule will give us an a prime term, a comma I term times this, and this the same, left the same, and this one differentiated. that produces exactly those two terms. Keep in mind that the omega is A times this. Okay? The omega is A times this. That's why that becomes this term because of the prefactor A in this. You see, you can write this as A times this, which cancels that thing, and therefore you get those two terms here. See, 1 over A times dx1 to dxn. Okay, we are almost there. Remember, the mission was to show that our definition of the divergence reduces to what we expect the divergence to be on Rn in the trivial case. And indeed, if A of x is equal to 1 for all x, and that would be the case that we have on flat ordinary Minkowski space in rectangular coordinates, then we would have that the volume form is just dx1 veg dx2 up until dxn, and this coefficient function A of x, the volume form is simply 1, because there's no curvature or non-trivial metric or anything. In this case, this formula for the divergence clearly reduces to something much simpler. Namely, the A is 1, this A is 1, this omega is just dx1 to dxn, and all we have here is psi I, psi I. So we have that the divergence of a vector field is really this. Psi I, I, which is to say, differentiate the first component function with respect to the first direction plus second component function with respect to the second direction, etc. Sum it all up. So it does what we expected. There's one more thing, though, that you have to keep in mind. When in electrodynamics, we first learned that this is the divergence of a vector field, summing up psi I, I, we skipped an important point. This looks as if it were a function. This looks as if it were an element of lambda 0, right? A function. But now we see it's not. It's an n form of which this is the coefficient function, right? So the divergence is really this n form, the right coefficient function, which is to say that when you use in electrodynamics the divergence, you can actually integrate it over all of the n-dimensional manifold. The reason being that it is an n form, not a 0 form. It also means, by the way, that if you go from a right-handed to a left-handed coordinate system, the divergence picks up a minus sign. A scalar function would not. Okay? An element of lambda 0 would not. So now that we have the divergence, we can derive Gauss's theorem from Stokes' theorem. Okay, so we have that the divergence is the Lie derivative of the volume form. It's a little awkward, but it gets the job done in a covariant fashion. It is an n form, so we can integrate it over an n-dimensional manifold. Trouble is that Stokes' theorem can be applied when what you're integrating over is the d of a differential form. Now, is the divergence the d of a differential form? It turns out it is. So the divergence can also be written in this way, because if you remember, the Lie derivative acting on differential forms is also the anti-derivative, the anti-commutator of the exterior and the interior derivations. I hope you remember that formula. You had so many, I don't know. maybe make a little list of the important formulas for yourself just to remind yourself of these things. So the Lie derivative on any differential form can always be written as this. This is another way to write the Lie derivative in the xi direction. Okay, let's use this formula. The Lie derivative takes this form and we apply it to a volume form in order to get the divergence. Now, since the volume form is an n form and there are no n plus 1 forms, the d on that is 0. So the second term doesn't contribute. And we are left with this observation. The divergence of a vector field is the d of the interior derivation acting on omega. So there's another way to get to the divergence. the inner derivation applied to omega is a very simple operation. You just take the tangent vector and plug it into the first slot of that n form. That's what the inner derivation does. Just take the argument, plug it into the first slot of that n form. Then you arrive at an n-1 form. Apply the exterior derivative on that, get an n form. That's the divergence of a vector field. It's another way of writing it. So now that we have that the divergence of a vector field is the d of something, is the d of a differential form, we can apply Stokes' theorem. Because remember, Stokes' theorem says that if you integrate the d of a differential form over a manifold, you get the same thing as if you integrated the differential form itself over the boundary. So this is the divergence of the vector field psi. If we integrate it over a region G, we get the same number as if we integrated over the boundary of that region the differential form itself without the d. Right? We just drop that d here, the co-boundary operator here, at the expense of getting a boundary operator there. So that is already Gauss's theorem. It says that the divergence of a vector field integrated over an n-dimensional manifold is given by the same number that you get when you apply the tangent vector as the first argument of the volume form and integrate that over the boundary of that region. So that's the abstract formulation of Gauss's theorem. We will later, in general relativity, come back to those things when we discuss conservation laws. Let me give you a bit of a spoiler there. There are no conservation laws in general. Right? Because energy conservation follows via Noether's theorem from time independence. If everything is always the same at all times, yeah, well, then that translates in the conservation of energy by Noether's theorem. And if everything is rotation symmetric, you get angular momentum conserved, and everything translation symmetric, you get the momentum is conserved. But of course, on a curved space-time, everything changes. Things can change over time. The expansion may be time-dependent. Curvature can be space-dependent. And of course, the universe may have different curvature in different directions. So nothing is really conserved. Now, two important circumstances, though, where we will need all of those theorems. One is we can make assumptions, simplifying assumptions. For example, it's a very good assumption or approximation to say that the universe is pretty much flat, isotropic, and translation symmetric on distances larger than like 1 billion light years. Things average out there, and we have, in effect, those symmetries, and in effect, we get conservation laws. And then the question is, what does Noether's theorem do for general relativity when you do have those symmetries? So we'll come back and use Stokes' theorem and these things to get conservation laws for those cases. And then there are those situations like colliding galaxies, where really we don't have conservation laws, but clearly something approximate, some other thing must hold. There must be some sort of trade-off between energy and momentum that's caught up in matter and what's being absorbed, so to speak, by curvature. And so we will then again use methods like that to find out how you can calculate, for example, for colliding galaxies, something similar to saying these are the kinetic energies going into the collision, these are the angular momenta, these are the momenta going into the collision, and you have something like a conservation law that tells you then how they will interact with each other. It's not going to be like in Newtonian mechanics, but this is the math we need for it. Mm-hmm.
That approximation take into account galaxies with supermassive black holes?
Does it take into account
black
what?
hole massive centers in the galaxy?
Oh yes, of course. Yeah, all of that. Whether the mass is in black holes or whether it is in dark matter or dark matter inside black holes. Yeah, all of this. Yes. Yeah. The math is agnostic about what the origin of the curvature is and what the origin of the mass and the energy is. Of course, there used to be also this school of thought which said that there may not be dark matter. Instead, it may be a modification of gravity. I mean, it's still being considered, even though the evidence seems to be shifting towards dark matter, definitely, instead of a change of the laws of nature. But in any case, you can see how that sort of equations will be useful and even necessary for that to study these things. Okay, so far we have differentiations, plenty of them. We have directional derivatives in the form of tangent vectors. We have the exterior derivative, the inner derivation. We have Lie derivatives, and we have the divergence of vector fields. And we figured out how to integrate. And we were able to do all of this without ever introducing a notion of distance between points. We have a notion of volume. We need it for Gauss's theorem and divergences, but we don't have a notion of distance between points yet. Given a differentiable manifold, there is no way to calculate what the distance between 2 points is. The coordinate distance is of no relevance, because change chart and you get a different coordinate distance. So we don't have any means yet of calculating the distance between 2 points. In other words, I'm not saying the distance is there and we just don't know how to calculate it. No. We haven't endowed the manifolds with a structure of distance yet. We haven't even defined what distance should mean on a differentiable manifold. We need to do that. So the problem is that the numerical distance between 2 points is coordinate system dependent. So we can't just use that. However, remember from special relativity something important, something that we will then carry forward using the equivalence principle to general relativity. So in special relativity, we have that if 2 events, P and Q, have coordinates x0 to x3 and x0 plus epsilon naught to x3 plus epsilon 3 in an inertial rectangular coordinate system, then their distance, their invariant distance, their coordinate system independent distance, and by that is meant the Lorentz transformation independent distance, then the Lorentz transformation independent distance between those 2 points is given by this sum and difference between the coordinate differences. This is not invariant as it stands under arbitrary change of coordinates, but it is invariant under changes of Minkowski rectangular coordinate system. It's invariant under Lorentz transformations. And this sum is conveniently written with this eta matrix, eta mu nu, which has a -1 in the 0, 0 position and then has 1s on the diagonal elsewhere, and other than that it's 0. It's this matrix. So that's the distance formula, the invariant distance formula that holds in all inertial coordinate systems for flat Minkowski space, of course. Now mathematically we could do all sorts of things, but for the purpose of general relativity, we now invoke the equivalence principle. By the equivalence principle, there should always exist local inertial coordinate systems, people freely falling, building coordinate systems with standard rods and standard clocks. This should always be possible, such that this is true, at least in an arbitrarily small neighborhood. So the equivalence principle says that, well, that's true for Minkowski space, but it should also be true for freely falling observers. And it may not be entirely true, but if the region which the freely falling observer is considering is shrunk smaller and smaller, then this formula should become more and more accurate. We therefore define metrics. We define that a pseudo-Riemannian metric, and I put it in bracket because the definition covers 2 cases, the Riemannian case and the pseudo-Riemannian case. We say that a pseudo-Riemannian metric on a manifold M is a covariant 2 tensor sorry, it's a covariant two-tensor field, G. That is, sorry, it is a map from the manifold into the covariant two tensors. This is a tangent space, right, with 0 up here, 2 down there. And it's not just any covariant two-tensor field. No, it's got to be obeying those conditions here. It must be symmetric. So if you take this covariant two-tensor field and you feed it two tangent vectors, you get a number out of it. And that should not depend, that number should not depend on the sequence in which you plug the numbers in there. I'm making this point in this way to say that it's coordinate system independent, this notion, and even index independent. It just says that it's a two-form, not a two-form, it's a covariant two-tensor, not a form at all, right? Because it's symmetric instead of antisymmetric, and it's symmetric in its arguments. And also, we need, and that's also very important, we require that this metric, this covariant two-tensor, has the property that if, when evaluated on two vectors, it is 0 as I run all those psi vectors through the tangent space, then that can only be true if eta itself is also 0. In other words, it doesn't have a kernel as a map. You can view this as a map. You can view the metric as a map from contravariant vectors into covariant vectors. Because if you plug in a contravariant vector, you get a covariant one tensor out of it. You get a tangent vector out of it. And as such a map, it's not allowed to have a kernel. So the metric is required to be non-singular, symmetric and non-singular. The non-singularity condition of it will allow us to define a volume form on the basis of the metric. Remember, a volume form is an n-form that nowhere vanishes. Now, there are two cases, Riemannian and pseudo-Riemannian. If the metric, in addition to being symmetric and non-singular, also is positive, if it always outputs a positive number, if you plug in the same tangent vector twice, if it's also positive, then this is called a Riemannian metric. Of course, in general relativity, the metrics will not be Riemannian, it will be pseudo-Riemannian, because the distances can be negative. Remember that the distances, the space-time distances between two events can be space-like or time-like. And in the time-like, it would be negative by the convention that we adopt here. So a differentiable manifold together with a Riemannian or pseudo-Riemannian metric is called a Riemannian or pseudo-Riemannian manifold. Now let's look at the metric in a basis, finally. And at this stage, I want to make a point of not choosing the bases in the tangent and cotangent vectors that come with the coordinate system. Because really, the metric has nothing to do with coordinate systems, right? So let us choose just some arbitrary basis now to write down the metric. Very important. So let's assume that the theta I are a choice of bases in the cotangent space. You may, if you want to, choose your theta I to be the dxi. But you don't have to. Remember that at every point of the manifold, you have a cotangent space, which is an Rn, which is a vector space. You get to choose what basis you want to use there. And so we have now for the theta I are a basis-valued function. Okay, so for every point on the manifold, you get to choose another basis. This is a possible choice, but there are infinitely many other choices. So assume that the theta I are bases in the space of one forms, that they are a basis in the cotangent space. Then the tensor product of those basis vectors forms a basis of the space of covariant two tensors, and therefore the metric can be expanded in that basis. So the metric tensor is up to coefficient functions gij, which are elements of lambda 0 or just f of m, they're just scalar functions, times these basis vectors of the space of covariant two tensors. Now let us make a choice for the tangent vector space basis. Well, we've already made a choice in the base, for the basis of the cotangent space, the thetas. Let us choose the dual basis for the tangent space. Again, you would be free to choose another basis, but in this case, it just makes things more complicated if you don't choose the dual basis. So let us choose the dual basis. The dual basis vectors are tangent vectors chosen such that when you apply the cotangent vectors on the tangent vectors, when you apply this basis on that basis, you get just the delta I R. This is the dual basis to a given basis. Again, if you wanted to choose the dxi as the thetas, then the dual basis would be the d by dxi, but no need to make that choice. So now, finally, we get to the components of the metric. Okay? The metric tensor is a covariant symmetric two-tensor. It feeds on two tangent vectors. Choose your basis vectors. If you plug the two basis vectors into the metric, you get a number out. Namely, if you use this formula up here, you plug the two basis vectors into your metric, then this evaluates to a number using the Kronecker IR, and here that evaluates to a number, Kronecker JS. Summation, you just get GRS. And so what you see is the GRS, which is a number-valued function, is really a number-valued function. This is not a tensor. This is a function on the manifold. The G is a tensor. That thing up there is a tensor. This matrix of coefficients is a matrix whose matrix elements are just functions on the manifold, scalar functions on the manifold. And if you choose a different basis in your tangent space, then the very same metric gives you different matrix of entries. Okay? So the matrix that the metric is represented by depends completely on the choice of basis that you make. And remember that that choice of basis, in principle, has nothing to do with your choice of coordinate system. Now, a manifold is called a Lorentzian manifold if at all points in the manifold there exist bases E such that this matrix by which the metric is represented is the eta ij matrix. Now please don't confuse this with a statement that you've probably heard in an earlier course on general relativity, where you've probably heard that you can always find a coordinate system such that the metric takes this form at a point, but generally not elsewhere, just at a point. You pick a point, there's going to be a coordinate system in which the metric takes this form at that point, but elsewhere it takes some other form. That's not this statement at all. This statement says that your manifold is Lorentzian, qualifies for general relativity, therefore. Your manifold is Lorentzian if the metric takes this form everywhere at once. On the entire manifold, the metric has this matrix representation everywhere at once. The statement is that there exists a basis for each tangent space such that in that basis the metric takes that form. In general, that basis will not be the basis of the d by dxi. It will be a more general basis. But that it exists, you can deduce from what you've heard earlier in GR. Remember, there was this statement that you pick a point, arbitrary point of the manifold, there's always going to be a coordinate system in which, at that point, the metric takes this form. Okay, let's take this for granted. What that means is that if you choose that coordinate system, then the basis of d by dxi the basis of the tangent vectors in that coordinate system, when you plug that in here, you get the matrix has this form. Okay, so you take a note of this. Aha, I should choose, for this particular point, I should choose these basis vectors that come with that coordinate system. And then you go to another point. And then again, there is a coordinate system in which the metric at that point takes this form. Record which basis vectors were used for that purpose. And so on. You can do that for every point of the manifold. So really, for every point of the manifold, there is a choice of basis for which the metric takes this form. You may wonder, why bother with this? What's the benefit of being able to write the metric tensor as this eta, just like in special relativity, everywhere? Clearly, there's a price to pay. What is it? And how expensive is it? Clearly, there is a simplification to be gained if the metric tensor is always that, but what's the price we have to pay? Well, the price we have to pay is that now there's no more information in the way that the metric tensor looks. All the information is now elsewhere. It's in how you specify your basis. Right? For example, a coordinate system comes with the basis of d by dxi. The basis that diagonalizes the metric is a different one. The change of basis matrix from the basis that comes with the coordinate system to the basis that diagonalizes the metric, that change of basis map, as we will see later in the course, carries now all the information about the manifold that used to be encoded in that matrix in here. So why would we bother? I mean, it's like we're just shifting the level of difficulties around. We make the representation of the metric trivial at the expense of having a highly non-trivial choice of basis then. But the reason is, the reason why this is very often useful is, on one hand, it's to see that general relativity can be formulated as a gauge theory. You see, it's not unique. It's only unique up to a Lorentz transformation, the choice of bases that will diagonalize the metric. And that non-uniqueness is the gauge principle for GR. But secondly, if you want to write down, for example, the Dirac equation, and I'm just previewing what we will do later on, if you want to write down the Dirac equation on a curved space-time, then you're faced with the problem of the gamma matrices. And the gamma matrices for the Dirac equation are defined in terms of their anti-commutation relations. They anti-commute, and on the right-hand side of the anti-commutator is the eta of special relativity. If we didn't do this trick, if we let the metric always be represented in the basis which comes with the coordinate system, well, then this matrix changes all the time, and then we need different gamma matrices at every point of the manifold. That would be an infinite mess. Because at every point of the manifold, you have to find a new representation of the gamma matrices. So for example, for that purpose, it's very useful to choose your basis vectors always such that the metric takes this trivial form at the expense of having non-trivial change of basis functions around. And then you can at least write down the Dirac equation in a straightforward way. All right, that's all for today. I see you on Monday then.